Okay, so what we have today is, or what we're going to do today is we want to explain or show that functions of the form exponential to the negative alpha k squared t k x. We want to show that functions of the form exponential of negative alpha k squared t for time times exponential of I, that's supposed to be an I, sorry, kx are solutions to this partial differential heat diffusion equation. And what this is it's a partial differential of temperature with respect to time is equal to alpha times the second derivative of time, or temperature, I'm sorry, with respect to x. And so I hope it's okay that I'm using OneNote today to draw this stuff out. I moved to back home, I guess, because my lease was up on my house, so I don't have my whiteboard to derive this stuff out. So it might look really, really, really gross as I write it all, but I hope that's okay, and I hope we can make it through this together. So what we have is the equation, the exponential of I, which is an imaginary number. Ix is equal to the cosine of x plus I sine x. And so for the Taylor series expansion of e to the x, I'll write all the Taylor series expansions in green here. Because we're going to write out for e to the x, cosine of x and sine of x. So what we have for the Taylor series expansion of x is we have e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And then for cosine of x, we have that the cosine of x, again, Taylor series expansion, is equal to 1. Also, cosine and sine alternate, so I'll incorporate that in. But we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and this continues on for however long or however many terms you need it for. And then for sine of x, we have that 1 plus x, 1 minus x plus x cubed over 3 factorial minus x to the 5th over 5 factorial. And this continues on, and all sine, can I type this one? Sine is the odd terms, and cosine is all the even terms. So if we bring I, or the imaginary number, into this equation, we can say again that, let's pan down. When we can say that the cosine of x plus the imaginary sine of x is equal to e to the I sine of x, or imaginary sine of x. But what we want to do is we want to say that if we write that temperature is equal to exponential of I k x times exponential of negative alpha k squared of t, what we want to do is we can say, or we want to be able to say that if we plug, can I scroll up? Oh goodness. If we plug this in for t in both of these equations, or both sides of this equation, that this is an appropriate solution to the partial differential equation, or heat diffusion equation. And so when we incorporate that in, we'll start with the left side. We get that after taking a derivative, we get that the left, negative alpha k squared of e to the negative alpha k squared of t, because on the left we took the derivative with respect to time, or little t. times e to the ikx. And then on the left, we have to take the derivative twice. We get that, I'll do this one in purple. Whoa. We can say that the left is equal to alpha k squared. No, not alpha k squared. Alpha, because we're taking the derivative with respect to x on the left, on the right side. To the negative alpha k squared t times I squared k squared of e to the ikx. Note that I is an imaginary number and I squared is equal to -1. And so if we could incorporate that, we get that the left side, let's do moving, again, we're going to turn this into -1 and we're going to move the k squared over here. So we get that the left side is equal to negative alpha k squared e, or exponential of negative alpha k squared t times exponential of I k x. And if we lasso select this left side and move it down here, we can see that both sides of the equation are equal. And since both sides of the equation are equal, that means that when we use the expression that temperature is equal to exponential of ikx times the exponential of negative alpha k squared t for time, and take the derivative for any k value. And in these equations, or this expression, k is an integer. So let's type k is equal to any let's not do all caps. Any integer from 1 to whatever number, so long as it is an integer. Any number that is an integer. And so since this is the case, and since, again, both sides of the equation are equal, that means that this expression is a solution to the partial differential heat diffusion equation for T, or when we use T as a solution in this equation, or this as a solution equal to T in the equation.